Okay, everyone. So today we're going to look at the last section in chapter 11, which has to do with three more gas laws. So up till now, we would have already looked at Charles's law, which looked at temperature and volume. So we're going to look at Boyle's law, Gay-Lussac's law, and the combined gas law, which kind of makes sense because we're going to be combining the different laws together. Okay. So the three main variables that are involved with gases are temperature, volume, and pressure, okay? So we've already looked at temperature, volume. The rest of the relationships we're looking at obviously are different combinations from the others. So first, let's take a look at pressure and volume. So pressure and volume share an inverse relationship. So what that means is when one goes up, the other goes down, and vice versa, right? So when pressure goes up, volume is down. When pressure goes down, volume is up. So this should actually make sense. Actually, before we even get to that, going back to the idea of the gas inside of boxes, right? So let's say I had two boxes that has the exact same amount of gas. Okay, and let's imagine that the temperature is the same. So if this is 25 degrees Celsius, so is this one, okay? But what's different here is obviously the size of the container that the gas is being held in. So remember when we talked about pressure, we talked about how it has to do with the number of collisions that that gas is undergoing. So let's say this is A versus B, right? So our A gas is going to have a higher number of collisions simply because we have that gas in a smaller space. So it's going to be bumping into things way more. So the pressure is up. So the reason why the pressure is up in this particular case is because the size of the volume that we're giving the gas is smaller, right? And then vice versa here. We've increased the volume. So what ends up happening is the pressure is going to go down because we have a lower number of collisions. Right, lower pressure. So taking a look here, right, this is showing you the same thing, right? So if you have two different gases, you have a low pressure versus a high pressure, look at the volume that the gas is occupying. So it's the same amount of gas in both containers here. It's like a piston that has a movable lid to it. Basically, this lid can go up and down. So when you give it a large amount of space, the volume is large, the pressure is down, and then opposites. If you give a small amount of space, you're going to have a high pressure. So this relationship is called Boyle's Law. Okay, so the relationship is exactly what we were talking about before. As the pressure on a gas increases, the volume of the gas will decrease, provided that the temperature and amount of gas remains constant. So of course, because we know temperature can change the pressure and change the volume of something as well. So we're assuming every other condition is the same. The only thing that is changing is the volume and the pressure, right? So here is our formula. So P1, V1 is equal to P2 and V2. So remember your P1, the ones basically are like your initial or your starting point. The twos are your final. Okay, so normally you have something that is changing and then you have an end result of that change. Now, just like with the other law that we looked at, you will always have enough information for 3 out of these 4 variables. So maybe sometimes you're missing V1, maybe sometimes you're missing P2. But the point is that you will have enough information where you're only solving for one thing. Okay, so one thing to keep in mind is that the units must be constant. So what that means is if your volume is in milliliters initially, it needs to be milliliters finally. If it's liters, it has to be liters. Whatever the unit is on one side of this equation, the unit must be the same on the other. So more importantly, that goes for your pressure. So remember, pressure comes in a whole bunch of different units, right? kPa, we have torr, we have millimeters of mercury, and then we have atmosphere. So actually, it literally does not matter which one you have. If I have atmosphere in P1, my P2 is going to be atmosphere, okay? if the question gives you two different pressure amounts, you have to convert one. And remember, we went over the conversion in one of our first few lessons in this chapter, right? So if you have one as ATM and the other one as torr, you will not be able to mathematically calculate this. You need to have the units be the same. It doesn't matter if they're torr, it doesn't matter if they're ATM, but they both have to be the same. That's the key. Okay, so this is a graph just basically showing you the relationship here. So this is an inverse relationship. So very different from when we looked at Charles's law when it was a direct relationship, a linear relationship, right? So if you take a look here, when the volume goes down, right? So let's say the volume was here and then the volume is here, right? Went from like, I don't know, 900 to 300, the pressure has gone up. And if you were to look in the opposite way, if you started at 300 and you went up, the pressure went down. Right? So it's an inverse relationship. Okay, so let's take a look at the sample problem. So we have a 2-liter party balloon at 98 kPa that's taken to the top of a mountain where the pressure is 75 kPa. So this pressure was the pressure at the bottom of the mountain. The top of the mountain is now 75 kPa. Assume the temperature is the same. What is the new volume of the balloon? Okay, so we have our initial volume. We have our initial pressure, 98 kPa. We have our second pressure at the top of the mountain. And we want to know what is the volume at the top. So one thing you want to check to make sure that your units are consistent. So both of them are in kPa. We have our volume in liters. That means that this final answer will also be in liters. Right? So our formula is P1V1 is equal to P2V2. And we're simply going to plug in. So you can plug in before or after, but you're going to get the same result no matter what. So we have 98 kPa times 2 liters is equal to 75 kPa times V2, right? So to get V2, we need to divide by the 75 to get the V2 alone. Right, so that cancels, and then look at the units, right? We're left with units of liters, which makes sense. So if we calculate this out, we have 98 times 2.0 divided by 75. So this is 2.61333333 liters. For significant digits, we're doing only 2, right? So if you look at all the numbers here are actually 2. So 2.6 liters. All right. So pretty straightforward. They're very similar, right? It's just instead of volume temperature, it's pressure temperature, pressure volume. The next one that we're looking at is pressure temperature. I went ahead of myself. Okay, so we've looked at two combinations. We've looked at temperature and volume. We've looked at pressure and volume. Our last one here that we're looking at is Boyles Law, which is temperature and pressure. Okay. So this should make sense right off the bat that if you were to increase the temperature of a gas, we know that the gas is going to move faster, right? So you have more kinetic energy. So let's imagine for a second if volume, assume that the volume is the same. So imagine that these two containers are the same size, A and B. Okay, if I have the same amount of gas in both containers, right, except one is at a higher temperature, right? What's going to happen here is obviously all particles are in motion, but the one that is 75 degrees Celsius, or the one that's hotter, is going to have a lot more energy. They're bouncing around a lot more inside of that container. So what ends up happening is, remember the key is the number of collisions will directly affect the pressure. So if we have more collisions, you have more pressure. So hopefully you can it would make sense that the one that has a higher temperature has a higher number of collisions because they're bouncing around so much more than it would be at the 25 degrees. So in this case, we actually have the same linear relationship where If we increase the temperature of a gas, the pressure of the gas will also increase, and vice versa. If temperature decreases, right, the particles are moving around a lot slower, which means the pressure is going to decrease, right? So this is why when you have a container like this hairspray container, right here, is that it has a lot of warnings on it that it might explode if it reaches a certain temperature. It's because the gas that's inside is going to be reaching such a high pressure. It's putting a lot of, there's a lot of collisions happening with the wall, and it wants to basically escape this container because it's pushing so hard against the metal container or whatever it's made up of. So it has the possibility of exploding. So obviously that's why you see those heat warnings. Okay, so this is Boyles law. So we know pressure and temperature are directly related. It's a linear relationship, very similar to when we looked at volume and temperature. So we have P1 over T1, P2 over T2. Reminder, your pressures must be the same unit, just like we just saw in that last one. So if it's both kPa, that's fine. If they're both atmosphere, if they're both torr, that doesn't matter. It just matters that they have to be the same. Also, your temperature must be in Kelvin. So that means, remember, we'll take our degrees Celsius and we add 273 to it. Any gas formula that we're using, no matter what, if there's temperature involved, it is involving kelvins. You cannot have a negative temperature. Okay, so in terms of a graph, right, so we have, again, a linear or directly proportional relationship between pressure and temperature. When temperature goes up, right, so does the pressure, and vice versa. All right, so we'll do an example, and then I'm going to have you try one out. Okay, so a sealed storage tank contains argon gas at 18 degrees Celsius with a pressure of 875 kPa. What is the new pressure if the tank and its contents warm to 32 degrees during the day? Okay, so we have temperature 1 of 18 degrees Celsius. I'm going to convert this right away. So we do 18 plus 273, which is 291 Kelvin. And the pressure with that temperature is 875 kPa. Okay, we are looking for the new pressure. So we don't have that yet. But we do know that it's 32 degrees Celsius, which means we're going to do 32 plus 273, which is 305 Kelvin. All right, so we have P1 over T1 is equal to P2 over T2. So again, like with all of these, you're going to have enough information where you're only missing one. So we have 875 kPa over 291 Kelvin is equal to P2 over 305 Kelvin. Okay, so we are going to cross multiply these. So we end up getting P2 times 291 Kelvin is equal to 875 kPa times 305 Kelvin. And remember, you have to get rid of that. So that way we have only P2 on that side. Right, and that should make sense, right? The unit of Kelvin will cancel and we'll be left with kPa. So this ends up being 875 times 305 divided by 291. So this ends up being 917.096 kPa. And then for sig figs, it is 2. So it's 920 kPa. Okay, so give this next one a try. And then in the next video, we'll take this up. So actually it worked out perfectly. This is the end of part 1. Okay, so give this a try and then check out the answer in the next part.